Today, we're pulling back the curtain on the invisible force that powers pretty much everything in our lives. We're going to demystify the fundamental, the elegant, and the absolutely essential shape of electricity, the sine wave. Think about it. You plug stuff into the wall every single day. But have you ever stopped to wonder, what does that power actually look like? If you could see it, what shape would it have? Well, that's exactly the question we're going to answer.
Visit youtube.com/avidsystem and don't forget to subscribe.
So to figure that out, we first have to understand what kind of electricity is even flowing through our walls. Because, not all electricity is created equal. It really is a tale of two very different currents.
On one side, you've got direct current, or DC. It's direct. The flow is steady, always in one direction, kind of like water flowing through a hose. That's the power you get from a battery. But the power in your walls? That's a different beast entirely. It's alternating current, or AC, and just like the name says, it's constantly alternating its direction, flowing one way, then the other, back and forth, over and over again, many times a second. Okay, so if AC power is always changing, how do we even begin to visualize that? Where does this distinctive wave shape we're talking about actually come from? The answer, it turns out, is beautifully simple, and it all starts with something we see every day: rotation. To really get this, picture a single dot on the edge of a spinning wheel. Now, as that wheel spins at a constant speed, imagine it's also moving forward. If we only pay attention to the up and down motion of that dot, what do we see? We see it rise smoothly to a peak, fall back through the middle, dip down to a low point, and come right back to the center. That path it traces, that is a perfect sine wave. It's this incredible link between the physical rotation in a generator and the electrical wave it creates. And that's really our official definition. The sinusoidal waveform, what we all call a sine wave, is simply a picture of alternating current. It's the natural shape of electricity that comes from a rotating generator, and it is the most fundamental waveform we use to power our world. All right, so now that we know what it is and where it comes from, let's, take it apart. Let's look at its anatomy. Just like any shape, it has a few key features that define exactly what it is. First up is amplitude. This is really just how tall the wave is, its peak height, measured from that center line. And if we go back to our spinning wheel analogy, the amplitude is simply the radius of the wheel. A bigger wheel gives you a taller wave, which means a higher voltage. It's basically the wave's intensity. Next, we have something called the period, and this is all about time. It's how long it takes for the wave to complete one full cycle, from the start up to the peak, down to the bottom, and back to where it started. In our analogy, it's just the time it takes for the wheel to make one complete rotation. Simple as that. Now, tied directly to the period is frequency. If the period is how long one cycle takes, frequency is how many of those cycles happen in a set amount of time, specifically in 1 second. We measure this in hertz. So when you hear about the 60 hertz power in North America, that means the wave is completing 60 full cycles, or our wheel is doing 60 full rotations every single second. So it's really important to think of period and frequency as two sides of the same coin. They're inverses. A wave with a long period, where each cycle takes a while, is going to have a low frequency. And a wave with a really short period, well, it's going to have a super high frequency, because a ton of cycles can fit into that 1 second. So we can see the wave, we can name its parts, but how do we describe it precisely? What we need is a kind of recipe, a formula, that can tell us everything we need to know to build one specific sine wave. Now hold on, don't let the equation intimidate you. This is not some scary, complex math. It's just a shorthand recipe. Think of this formula as the universal set of instructions for any sine wave you can imagine. And each part relates directly back to what we've just been talking about. So let's break down this recipe. AT is just the height of the wave at any given moment in time, t. AM, that's our amplitude, the peak value, the radius of our wheel. The sin function is the secret sauce. It's the part that turns the rotation into that perfect wave shape. And that little omega symbol, omega, that's just a technical way of describing how fast our wheel is spinning. With just these few ingredients, this recipe lets us draw that exact wave. Okay, so this brings us to a really practical, real-world problem. If the voltage of a sine wave is constantly swinging from a positive peak to a negative peak, and it's literally zero twice every single cycle, how do you assign a single, useful number to it? how do you measure the power of something that's always moving? Well, here's the catch. If you just try to calculate the average value of the wave over one full cycle, you get a big fat zero. The positive half of the wave perfectly cancels out the negative half. So a simple average is totally useless. It tells us nothing about the power it can actually deliver. And that is the key question for pretty much any real-world application. We can't use the peak value because it's only there for an instant, and we can't use the average because it's zero. We need a way to find its effective, its truly useful value. And the solution is a pretty clever mathematical tool called the RMS, or root mean square value. Now, don't worry about the name. What matters is what it is. The RMS value of an AC wave is the equivalent DC value that would produce the same amount of power. It's the practical apples-to-apples number we've been looking for. So how do we find it? Well, for a perfect sine wave, like the ones we've been looking at, there's a simple conversion factor, a magic number, a shortcut. And that number is approximately 0.707. And here's where it all comes together. You simply take the peak voltage of the wave and multiply it by 0.707 to get its effective, or RMS, value. This explains something you might have heard of. That standard 120-volt outlet in your home, it actually has a voltage that's swinging all the way up to a peak of about 170 volts. That 120 number that you always hear about, that's the RMS value, the effective, usable power. So there you have it. From a simple spinning wheel to the effective power coming out of your wall socket, the sine wave is the natural, fundamental shape of AC power. But here's the thing. It's also the simplest, which leaves us with one final thought. What other electrical waveforms are out there, and in our complex world of modern electronics, why do those different shapes matter so much?
Thanks for watching.